Hello and welcome to the lecture Generative Adversarial Network Part 1. In this lecture, we are going to introduce the Generative Adversarial Network. Then we discuss the GAN architecture. Then we try to define the GAN loss function. And finally, we conclude this lecture by understanding the training procedure of Generative Adversarial Network. Today we will start Generative Adversarial Network. Generative Adversarial Network, popularly known as GAN, is a generative model which can synthesize that realistic data. By definition, generative adversarial networks or GANs are a class of machine learning frameworks where two neural networks, namely generator and discriminator, are competing in a zero-sum game to create realistic synthetic data such as images, videos, audios, etc. So by definition, what we can see that in GAN there is a two neural net in place. One is called generator, one is the discriminator. And I will see what are the roles of generator and discriminator in this GAN, how they are being trained, what is their target, and by virtue of these two neural net, how generative adversarial network as a whole create this realistic synthetic data and how it been converged. So GAN is basically a neural network that trained in an adversarial manner. What does this mean? There is some adversary. We'll see discriminator. This is another neural network that is going to play some kind of adversary. That is going to say maybe that what is being generated is look like realistic or is not, is like just generated, is not realistic. Some kind of idea that we will see later. So what is the goal of generative adversarial network? The main goal that they will going to create realistic synthetic data mimicking some distribution. What does this mean? That this data, what is the generated data, that is going to form a distribution which is very close or very similar to a given distribution. Let's see. Now this is a naive or a very normal GAN architecture. In this architecture, you can see two things. One is generator, one is discriminator. That we have said earlier. Now what is the input to the generator? This Z is a random noise, the Gaussian uniform noise. So you can say Z is basically coming from latent random space or variable Z. So you can also thought Z can be thought as a latent representation of image. Okay. So with this input, generator is going to generate samples. So these generated samples from a distribution of P of G. Okay. And these are the samples G of C. There is another kind of data set express that is real world, that is a true data distribution, that is existing data, and that will give you the real samples. Real samples are X. It is drawn from this P data distribution. So P data is a real sample distribution. Now these two are input is coming. That is the real data, it's a fake data. What is the role of discriminator? Discriminator is going to understand are going to discriminate between real data and fake or generated data, the real samples and generated or fake samples. So its job is correctly identify what is real and what is generated or fake. D of x is equal to real, D of z is fake. And based on this classification is adversarial loss. And this adversarial loss is being computed and being backpropagated to both discriminator and generator for their weight updation or for training. We'll see that these are done separately. When discriminator is being trained, generator is freezed, and when generator is trained, discriminator is that we'll see later. So this is as a whole the GAN architecture. The next question is that how this generative adversarial networks works. So as we have said, there is a two neural net in the GAN. So first of all, generator G, it starts from random noise. That means random noise is being input to the generator, and it generates fake data. That means the images that is generated by generator is a fake. We say it's a fake. It's not a real sample. It's a generated sample. But what is the target of generator? Generate fake data such a way they looks like real data. Okay. Next is the discriminator. What is the input to the discriminator? The real samples from the real data set, as we have seen here, that real samples from the real data set, and the generated samples from the generated data set. So this is the two. These fake samples from the samples generated by generator. So these two are input. And what is the role of discriminator? That evaluates data to distinguish between real and fake data. That is going to it trying to understand. It is coming from here, and these real samples and the generated samples, and discriminator have to discriminate between it is a real data or is a fake data or generated data. So next, what we have understood about adversarial learning. So adversarial learning is basically done by discriminator. So the objective of the discriminator is to correctly classify between real and fake data. And then they compute the adversarial loss. And this adversarial loss is backpropagated to both discriminator and generator, such that discriminator take this adversarial loss and updates their weight parameters. That means it learns to improve the classification accuracy between real and fake data. On the other hand, this adversarial loss coming to the generator, and generator will update weight parameters or learns such that it generates more realistic data samples, more similar to the real samples. So what we have to understand here, that the target of this discriminator and generator are not same. Rather, it somewhat competitive. Discriminator try to differentiate between real data and fake data, and generator on the other hand going to produce fake data in such accuracy so that discriminator cannot distinguish between. So it is competing to each other. Okay? And by competing in these two, what we'll see that will generate more accurate image or the data synthesis. Okay. Now what is the objective function of discriminator? That if it's a V of D or D for discriminator, G for generator. So it correctly classifies real as real, fake as fake. So to maximize discriminative efficiency, this is the objective. So that is the max of D of V of. This is the for the discriminator. For the generator, try to fool discriminator. So to minimize its discriminative efficiency by generating samples more close to real samples. So what it's required to minimizing this. That is the rule target of the generator. So as a whole, what is the objective of GAN? It's kind of a mini-max game. Mean of generator, max of discriminator. So this V of DG is basically this objective, that GAN minimizing the generator, maximizing the discriminator of V of DG. So this is the basic objective of the GAN. So here we can see an example of GAN. Here the real data set is from MNIST data set, that handwritten digits, and there is that's one sample that it look like so. This is the real sample. Now there is a random noise Z, and this is the generator that will take this input and generate something like this. Definitely this is looks kind of fake, because now this generated samples from a distribution as we have seen. Now this real sample and this generated sample are fed to the discriminator. What is its job? To find out if this coming, that is real. If this generated samples come, it's called fake. And based on this accuracy, the adversarial loss is being computed. This adversarial loss are back propagated discriminator as well as generator. This discriminator, by virtue of this adversarial loss, it updates weights such that it efficiently or more efficiently distinguishes between real data and fake data. On the other hand, generator use this adversarial loss so that it creates more realistic predicted samples such that discriminator fails to distinguish between which is real data, which is fake data. So this is the as a whole the GAN architecture. In this way, when it is convergent, when basically distinguish cannot understand that this is predicted or fake. That is our goal, because what we need at the end of the day, we need to synthesize or generate some samples which is not a part of or a member of this sample space, but it looks very similar or looks very realistic. Okay, so this is the GAN architecture, and this is a simple example to understand the GAN architecture. Now we are going to define the loss function of generative adversarial network. As you see, it is a similar diagram, but this is the real data set with data distribution P data x, from where this x is coming, that is the real sample, and this is the latent distribution or Pz of z. This is input to the generator, and generator generated this generated samples belongs to P of g. Now what is the target of GAN? Is basically try to generate the sample such that this P of g is very close to the P data of x, the real distribution. This generated sample distribution is close to the real distribution. Now what is the role of discriminator here? This d of theta d means parameter theta of discriminator. It is going to the real data and fake data. They distinguish between real and fake, and based on the adversarial. And the generator, it takes the z, the random variables input, and this is the parameter of this generator. So as a whole that we have discussed so many times, this is the. Now what is the loss function of this? Now here we use the binary cross entropy loss, L of y hat y of log of y hat plus 1 minus y log of 1 minus y hat. So the label for the data coming from p data x is equal to y is equal to 1, because what is this saying? That if the data coming from this real distribution, then the label, the corresponding label is 1, because real is 1, we assume the real is 1. And what is the y hat? Y hat is the generated. So this is basically that it is coming from generated. Okay. So what is basically we trying to say, that so putting them we obtain what will go into this, that in this loss function that we get d of x, that is the discriminator output of this real data when it is coming from real, that is log of dx. That basically this is the loss function. So what is text? It is the discriminator. This is the dx. Okay. So this is L of. So this is our what basically predicted, and this is the target, and the difference is this log. And if the data coming from generator, so it is now coming from here. So what is the data? Z of z. So generator, the label is y is equal to 0, because y is equal to fake. That means y is equal to 0 means fake. And what is y bar? D of g of z. So here the role of discriminator, previously the role of discriminator is that they get this data bar. If it is coming from real data, we have it have to say, the discriminator have to say it is y. If it is coming from the d of c of z predicted, then this is y is equal to 0, that means fake. So in this case, this loss is kind of this minus 0 log of 1 minus d of g. So this is what. So this we get these two equation from this cross entropy loss. Right? Now the objective of the discriminator is to correctly classify fake versus real data set. So that is the objective of discriminator. So from this a and b equation, what we get, that L of dx 1 log of dx is a log of d of g 0 is basically log of 1 minus d of g of g. And what is from the, just think from the discriminator point of view, that both the case we want to maximize, because what we required that this thing, they can, when a data coming from d of x, it says it is 1. When data coming from d of z, it says it is 0. So the what is required, how can we maximize both a and b? These two performance we have to maximize by making dx equal to 1. If this is 1, definitely it is said that y is equal to, that is our intention, that say dx is equal to 1. Okay, and then say d of g of z is equal to 0. If they predict this is 0, this is correct. If we predict this is 1, this is correct. So by making is equal to 1, we can maximize a, and by making d of z of 0, we can maximize b. So we have to maximize this log of dx plus 1 minus log 1 log of 1 minus d of g of z from the discriminator point of view. So if we think the loss function of the discriminator, this is the loss function. Now, what is the case of generator? The main objective of the generator is to fool the discriminator, or to make this dg of g is equal to 1. Now, you see that if you are going to correct it correctly from the discriminator, correctly classify, then this g of g is fake, so it should be 0. But what generator requires? Generator is basically try to fool the discriminator. Okay, so make dg of g. Why? For discriminator, all the values coming from generator should have y is equal to 0. So to fool discriminator, generator's role to produce such images which look like real. That means y is equal to 1. That is why we require this. So now when this y hat is d of g of z and y is equal to 0, then this is becoming L of this loss of d of g of 0, 0 log 0, so it is 0 plus 1 minus 0 log of 1 minus y hat. So ultimately it is log of 1 minus d of g of z. And to fool the discriminator, we have to make this d of g is equal to 1, that is. And how can we do that? We do this by making the minimizing this thing, because this thing is basically the efficiency kind of thing of discriminator. Now we want to fool discriminator, so we have to minimizing this, so that log of dx 1 minus log of d of g of c, we have to minimize. So if we can minimize it, we can above expression force to make d of g of z is equal to 1, which we want from the generator point of view. That is very important to understand. The previous slide, it is from discriminator point of view. That's why we are maximizing this expression. Whereas in generator, we are minimizing this expression. Why? This expression is basically saying the efficiency or accuracy of the discriminator. And what previously from the discriminator point of view, definitely we want to maximize the efficiency or accuracy. But from the generator point of view, since it want to make the discriminator full, it want to minimize this expression. So that, and if it minimize, then dg of g is equal to 1, which we want in the case of generator. So combining these two objectives, we can get this minimax objective function, mean of g, max of t, log of dx, 1 log of 1 minus d of c. This above expression for a single sample, because these are the single samples. And if we go for all samples, we take the expectation of above expression. This is just this x belongs to p data, real data space, and this z is for this random data space, and we can get generator of z and this. So this is the expression of the GAN loss function, that mean of g, max of d of v of d of g is equal to this expectation of x to p theta of log of dx plus subset of p of z log of 1 minus d of g of z. So this is, now we can understand how it is coming. This is exactly coming from this seminal paper of Goodfellow, Generative Adversarial Nets, IPS 2014. Okay. Now next is that this loss function, we just try to kind of summarize. Generator network try to fool discriminator by generating real looking images. Okay, discriminator network try to distinguish between real and fake images. Jointly, minimax came. The minimax objective function is this. Is basically that discriminator output for real data x, this, that thing. So you can say the discriminator, this thing, log of dx, discriminator output for real data of x, and this discriminator output for generated data in x. So what this discriminator want? This is the efficiency, these two. of this, so want to maximize. What are the generator want to do? That if generator want to fool the discriminator, so make it minimize this expression. And is expectation for all the samples, so it is minimized. So as a whole, this is the thing. So discriminator wants to maximize the objective such as dx close to 1 real and d of z is close to 0 fake. It is what. On the other hand, generator wants to minimize the objective such that close to 1 discriminator is fooled into thinking generator g is. That is exactly what the GAN is doing. So one very important thing to understand, what is doing here. Now you come back to this diagram. Now if both are doing, it is trying to fool the discriminator, it trying to efficiently. Now if both are parallelly doing or time by time, one separate way it is being trained, what is actually happening? It is generated samples. Initially, these samples is easily being detected as fake, but then it said that there is adversarial loss that drive generator to produce more realistic samples. So when the epochs goes, when this alternative training is done for many epochs, after that there will be a situation when discriminator cannot distinguish between this data and P data and these generated samples. And that is exactly what we required. We required to generate such samples that samples are looks very realistic and it looks like it's coming from the distribution P data of very realistic. But it actually is from this P of Z. So these two, then what does this mean? These two distribution become very much close or similar. That is the basic objective of the GAN. So by this loss function, what we have said that by this loss function we can achieve our target as a whole for the genetic adversarial network. Okay, so this is the GAN formulation, that mean of G, mean of max of D. This formatted as minimax game where we are trying to maximize this reward V of D of G. Generator is trying to minimize discriminator reward or maximize its loss. So this is the expression. Okay. So this is the idea of the GAN loss function or ultimately GAN formulation. Now we are going to understand how the generative adversarial network is being trained. So the training of GAN is basically divided in two parts. One is the discriminator training and another is the generator training. Now first we start with discriminator training. Here you can see discriminator is being trained by virtue of this adversarial loss. This adversarial loss backpropagated to discriminator, and discriminator basically using backpropagation algorithm updates weights so that it can more accurately distinguish between real samples and fake samples. So this is the discriminator training. One important thing to notice here, that when a discriminator is being trained, the generator is placed. It is not being trained, the parameters are not updated. On the other hand, when generator is training, now here also when generator is training, discriminator is fixed, its weights are not updated. Similarly, the adversarial loss is coming to the generator. It updates its weight parameters such that it can generate more efficient or more realistic samples, so that it looks like more real samples. Because that is the agenda, that is the goal of the generator. So try to fool the discriminator by generating a real sample looking. So it is being trained, and that time discriminator is present. So that is the generator training. Now is being taken from the paper of Goodfellow. Now this is the algorithm, the basic training algorithm, the mini batch stochastic gradient descent training, generative adversarial nets. Now what it is saying? Number of training iteration, how many iteration there? So for case steps, that being that m noise samples. So noise samples is Z1, Z2, Z10. This is the noise samples. Okay. Now from noise prior P of C of C. Same sample mini batch from m examples from the P data of X. P data of X. This is P data of X. That is the real data set. Now we are going to discuss the main algorithm given in the Ian Goodfellow paper in what he is proposed in 2014. Now here you can see that for the case steps they are basically taking the mini batch of m noise samples, that is the m noise samples from here, and m noise samples from the real data set as I mentioned, Z to Zm noise sample to Xm, the real sample. Now what done? Then the update discriminator by ascending its stochastic gradient. Because ascending, why they are ascending? Because it's a maximum optimization to be carried out with respect to t. It's for discriminator. So this is the loss function. They take the derivative of loss function like this, and that they are update discriminator by ascending its stochastic gradient. On the other hand, in the case of generator, they are update generated by descending its stochastic gradient because it is a minimum optimization, that is mean of this. So that is the major difference. Now if we see what actually happening here, now here you can see that this is the discriminator curve. Well, at the initial level discriminator performance also not good. This because this is the real data and this is the generated samples. So now discriminator is also some kind of fluctuating. That means it is not very good, well understand this discrimination. Now when discriminator is being trained, so what happened? Now you can say it is basically a very smooth curve. Now it can differentiate or distinguish between this P data X, this real, and this is the predicted data. Now we start training the generator. And when it is training the generator, that you could see this green curve is coming closer to the real data samples. So that means that it is coming, generator is still discriminating, but this discriminator is still discriminating, but it is close. And when it is almost converging, you can see these two curves, the P data X, this real distribution, this generated sample distribution almost coming, and then discriminator fails. And this is exactly the GAN points. And now you can see the GAN is converging. So in this lecture, what we have discussed, that we first introduced generative adversarial network, then we discuss the GAN architecture, then we understand what is the loss function of generative adversarial network, and we conclude by understanding the training procedure of the GAN. In the next lecture, we continue the generative adversarial network in the generative adversarial network part 2. Thank you very much.